All right, welcome ladies and gentlemen. This is video number 5 in our matter unit. So you're going to need to have your notes open to where it says video number 5. And something that you can use is a calculator. So if you have your phone out, you can just use the calculator app on that. That'd be great. So in this video, I'm going to be talking about conservation and how it applies to matter. So when you think about the word conservation, it usually means, if you think about like conserving wildlife or conserving water, it usually means to sort of to keep intact that almost that idea of zero waste, right? You conserve water means that you're not using excess water, that you're trying to keep the amount of water you use about the same. So that idea of conservation, of saving things, of keeping things intact, that's the same idea that we're going to carry over to chemistry. There is a lot of conservation in chemistry. There's a lot of conservation in science. So first up, we're going to talk about reactions a bit, and then we'll talk about conservation. So just as a review, a chemical equation, it shows a reaction. It writes out reactions and products, and it separates the reactions and products from an arrow, so by an arrow. So this is an example of a chemical reaction, 2H2 plus O2. Yields, that's always how you're going to pronounce the arrow that's right there in the middle, yields 2H2O. And the reactants are exactly what their name implies. They're the things that are doing the reacting in a chemical reaction, and they are always, always, always written on the left-hand side of the arrow. So everything on the left-hand side of the arrow, we always call that those the reactants. And they do the reacting. So in this reaction right here, the stuff that's on the left-hand side of the arrow is the big separator. These are our reactants. And then products are simply the things that are on the right-hand side of the arrow. They are called products because they are produced. You did not start with them. They're the things that are made over the course of the chemical reaction, possibly a new substance. So the right-hand side of the arrow, these in this reaction, the 2H2O, those are the products, and the arrow is always the big separator. So I always like to kind of draw a line down with the arrow to indicate that's the difference between where you start and where you end. Conservation. We've got so many laws of conservation in chemistry that I like to just kind of call law of conservation of whatever. And law of conservation of whatever always follows the exact same pattern. So be it mass, matter, charge, energy, they're always going to have the same sort of phrase. And they will always mean that whatever you start with, whether it's mass, matter, charge, energy, that's the exact amount of stuff that you have to end with. So the way that it's phrased is whatever you begin with, i.e. the stuff that's on the left-hand side of the arrow, i.e. the reactants, that is exactly how much of that thing, whatever your law of conservation is, that you have to end up with on the right-hand side of the arrow, i.e. your products. So law of conservation of fill in the blank. Whatever you start with for fill in the blank on the left-hand side of the arrow, that's exactly how much fill in the blank you have to end up with on the right-hand side of the arrow. And in terms of slightly more sophisticated jargon, we say that whatever you're conserving is neither created nor destroyed. And that's that idea of conservation, that you're keeping it exactly the same. Whatever you start with, you have to end with. You have to end with that exact same amount. The first law of conservation we're going to see is the law of conservation of matter. So that means that matter is neither created nor destroyed. And whatever matter you start with on the left-hand side of the arrow, you must end with the exact same amount on the right-hand side of the arrow. That arrow is always the indicator, sort of the equal sign, that separator between what you start with and what you end with. For us, in terms of matter, how we interpret in chemistry the law of conservation of matter is in terms of atoms. The total atoms that you start with on the left-hand side of the arrow must be equal to the total atoms that you end with on the right-hand side of the arrow. So that equals, that's really your arrow. That's your yields in a chemical reaction. Now, these atoms that you start with and you end with, they can totally be rearranged. You can move them around. You can bond them to new things. They can start with one guy and end with another guy. That's fine. But the total number of atoms that you start with and end with has to be the same, has to be conserved. That is the law of conservation of matter. So an example of this in terms of particle diagrams. We have two reactions we're going to look at. First up is Na plus Cl2 yields NaCl. We're doing this with particle diagrams, so we're going to draw some particle diagrams. So if I was drawing a particle diagram of Na, I could just do something like that because it's just a single atom and there's only one of them. Cl2, though, this is one of our diatomics, and it's a different atom, so maybe I'll use an open one, right? And so I'm showing that there are two of them, and they're connected. And then the arrow is a big equals, and then we've got NaCl. So now I'm going to do one dark and one open, and only one of each to indicate NaCl. Now if you look at what we've drawn, notice that we have one Na atom on the left, two Cl2 atoms on the left, but on the right hand side I only have one Cl atom. So this right now does not represent the law of conservation of matter, and so I need to fix this. I need to change this. So what I can do, I have to absolutely start and end with the exact same number of atoms. So right now this is not good. We don't like this in chemistry. It's not indicating conservation. But what I can do, the problem is that I've got two atoms of Cl2 of Cl on the left, but only one on the right. So I need to add more to the right. I need to make it balance the stuff that's on the left. But I can only add NaCl. That's the thing. That's the only substance that's on the right-hand side. I can't just randomly add a chlorine atom. I can't do that. I'm not allowed. The only thing that I'm allowed to do is work with NaCl. But I need a second chlorine. So what I'm going to do is actually add a second NaCl. Because again, that's the only thing that you can add on the right-hand side. The reactions doesn't have anything extra on it, so I'm only allowed to add an NaCl. And this will ensure then that my chlorines are now equal. They are now conserved. And now I have two NaCls. I've got one here and I've got one here, so I'm going to put a 2 out in front of the NaCl to indicate that I got two of those suckers. But now I've thrown off the sodium, right? I added a second sodium atom to the right-hand side, and I only have one on the left-hand side. The chlorines are all set, but the sodiums are not. So that's actually a relatively easy fix. I've got 2 on the left, 2 on the right, but only 1 on the left. So why don't I add a second one to the right-hand side and put that coefficient of a 2 out in front, and there we go. We've got conservation. Another example with ozone and oxygen gas, we've got O3 going to O2. Well, if I'm drawing O3 particle diagram, it will probably look like that, right? 3 atoms of oxygen. And if I'm drawing O2, again, it would be a diatomic. Right now, it's not balanced. It's not showing conservation of matter because I start with 3 oxygen atoms, but I only end with 2. I have to start and end with the exact same amount of oxygen atoms. So now we're thinking, when you have this issue of 3 and 2, it's best to think of least common multiple to get the number of atoms the same. So if I have 3 and 2, the least common multiple is going to be 6. So basically I want to make each side go to 6. So if I add a second O3 on the left-hand side and 2 more O2s on the right-hand side, now I have 6 oxygen atoms on both sides. I am obeying the law of conservation of matter. And if I'm putting this in terms of the actual equation, that would be I put a 2 out in front of the O3 to indicate 2 of them, and a 3 out in front of the oxygen to indicate 3 of those particles. But we also see law of conservation with mass, which says that the mass of the products is always equal to the mass of the reactants. We do not lose mass in a chemical reaction. Mass is neither created nor destroyed. Which means that when we look at a chemical equation, it's simply saying that the sum of the mass on the left-hand side is equal to the sum of the mass on the right-hand side. Whatever the mass of the reactants is in total, it must be equal to the mass of the products in total. And this is actually a fairly common Regents chemistry exam question. They actually like to ask this question. So an example is nitrogen and hydrogen react to form ammonia. If 14 grams of nitrogen reacts with 2 grams of hydrogen, how much ammonia will it make? So I've broken down the problem into a word equation. So we see right here nitrogen and hydrogen react. So that indicates that these guys are the reactants. So we've got them right here on the left-hand side of the arrow, and they react to form ammonia. So that means that that's a product, and it's on the right-hand side of the arrow. Notice that we don't even need to know the correct formulas. And it says then if 14 grams of nitrogen, what I like to do in these types of problems, I like to take this number and I like to write it underneath where it is in the reaction, so it's right underneath the nitrogen. 14 grams of nitrogen react with 2 grams of hydrogen. How much ammonia and I like to put a question mark to indicate that's what I'm solving for, will it make? Well, nitrogen plus hydrogen yield ammonia. Again, the arrow is always your massive equals sign. And for law of conservation of mass, it's saying that the sum of everything on the left-hand side must be equal to the sum of everything on the right-hand side. So for this given problem, if the mass of all the reactants added together is 16 grams, then that must be equal to the mass of the product. In this case, there's only one product, so we are going to be making 16 grams of ammonia. Looking at this with just one more problem, this one I ripped right off of an old Regents test, didn't alter it in any way. We've got this balanced equation below, represents reaction of glucose, right? We should know that molecule, with oxygen. The reaction is shown here. Determine the mass of CO2 produced when 9 grams of glucose completely reacts with 9.6 grams of oxygen to make 5.4 grams of water. Okay, the first thing that I want to say about this reaction, our arrow obviously is the big equals, but notice now that we have coefficients, the big numbers out in front. All right, remember that from the POGL, the coefficients, the big numbers out in front. A lot of students get thrown by coefficients in law of conservation of mass problems. I'm here to tell you these coefficients, they don't matter at all. They do not impact the law of conservation of mass. The law of conservation of mass does not care that there are 6 oxygens or 6 carbon dioxides or 6 waters. Law of conservation of mass simply cares that the total mass of the products must be equal to the total mass of the reactants. It doesn't matter at all, so don't let that throw you. So we've got some numbers in the problem. I'm going to kind of line them up with the thing they belong to. Determine the mass of CO2. Okay, so that means that that's my unknown. Produced when 9 grams of glucose. 9 grams of glucose. What's that? That's here. Right, 9 grams of that stuff. Completely reacts with 9.6 grams of oxygen. 9.6 grams of oxygen right there. To produce 5.4 grams of water. Match that up with the water. Okay. Great. Again, the arrow is the massive equal sign, and law of conservation of mass says that the sum of the masses of the reactants must be equal to the sum of the masses of the products. So just rewriting this out, 9 grams plus 9.6 grams must be equal to the missing mass, the mass that we don't know, plus the mass of the water. So then it becomes just simple, right? We can solve this. So if I sum this together, I got 18.6 grams is equal to the mass of the CO2, or your x, right? That would be your x if we're doing this like an algebra problem, and simply solve. If I just subtract 5.4 from both sides, that tells me that the mass that I'm missing, the mass of the CO2, is 13.2 grams. There you go, law of conservation of mass and law of conservation of matter. So again, we'll be practicing this with this in class.